Stripping down science. The Naked Scientists.
What can we do with that old plutonium? This week on The Naked Scientists, we'll hear about the new type of nuclear reactor that could use up our old waste as fuel. Plus, we'll discover the debate over using nuclear to plug our future energy gap. It's Sunday the 25th of March, and you're listening to The Naked Scientists with me, Ben Valsler, and I'm joined by Dave Ansell.
Hello. In the news this week, we'll focus on a camera that used a laser to actually see around corners. Find out how a simple blood test could tell you if you're going to have a heart attack, and discover what could be a cure for male pattern baldness.
So if you would like to get in touch with any questions or comments,
you can tweet at Naked Scientists, comment at facebook.com/thenakedscientist, or email chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Nuclear power has been firmly in the news this month as we mark the anniversary of the Fukushima power plant failure, the result of an earthquake and the tsunami that hit Japan on the 11th of March 2011. The Fukushima plant was commissioned back in February 1971, and reactor technology has developed considerably in those 40 years, with new designs being safer and more efficient. Even now, new breeds of reactor are capable of closing the nuclear cycle by generating electricity at the same time as dealing with the problem of radioactive waste. One of these is PRISM, that stands for Power Reactor Innovative Small Module, and that's been developed by GE Hitachi, and we are joined by their chief engineer, Dr. Eric Lewin. Eric, thank you ever so much for joining us. I wonder if you could start off by saying, what's the push to need this technology?
Ben, thanks for having me on your show. I would say the push is that as humans grapple with different energy sources going forward, the PRISM technology represents a different fuel source that has vast potential to generate a lot of carbon-free energy.
So what is the PRISM reactor itself, and how does it differ from a traditional nuclear reactor?
PRISM reactor is not too different from a conventional reactor in that it still does the basic fission process of breaking big atoms in half to extract energy. The PRISM technology came from work that General Electric started in 1981, and then the U.S. government funded a advanced liquid metal reactor program. And so at this point, the technology has really had 3 decades worth of development that we feel is ready to be commercialized in different market segments.
So how does it actually work? So we need, obviously, a radioactive source, but it seems that the PRISM reactor can use a far wider range of sources than the reactors that we're used to seeing. How does it take that reaction and turn it into useful energy?
Ben, what's unique about the PRISM reactor is that when a large atom, such as uranium-235 or plutonium, breaks in half or fissions, it gives off neutrons that are at a very high energy. And in our current commercial reactors with water cooling, those neutrons are slowed down or they lose their energy very rapidly. And that limits the amount of reactions you can do. So in the PRISM reactor, we use sodium as a coolant. That keeps the neutron energies still high or relatively fast, and that allows us to use different fuel to fuel this, and that's where the potential of this energy comes from.
So why would sodium allow things to remain faster than using water as a coolant? What's the advantage?
Well, as we know, water is made up of 3 atoms, oxygen and then 2 hydrogen atoms. And hydrogen atoms have 1 proton in the center, and they're about the same mass as a neutron. So when we have a fission reaction that occurs with water cooling, that neutron comes and strikes the proton in the water and slows down and gives off its energy because they're about the same mass. So it'll be similar to playing billiards where the cue ball, the white ball, hits the 8 ball and it transfers its energy. With sodium, because it's a bigger atom, it has 24 protons and neutrons in the center. When that neutron hits it, it typically bounces off and keeps its energy. So analogy that I like to use, if we look at the Earth's orbit, it takes us 365 days to get around the sun. the fast neutrons in a PRISM reactor would go around the sun if it followed that orbit in 73 hours. If we look at the slower neutrons in a water-cooled reactor, it would take 8.3 years. So it's a big difference in energy that we have, and that's why we can use different fuels.
So you're getting these sort of almost elastic collisions, and that means that you keep hold of a lot more energy. Does that also mean that if there's a problem, it takes you a lot longer to get rid of the energy to cool everything down?
Actually, it's kind of the reverse. When the PRISM reactor uses metallic fuel, it's in metallic cladding in a metallic coolant called sodium in a metal vessel called the reactor pressure vessel, and that allows us to have air come on the outside and to remove the heat. So when we look at the unique thing with any nuclear power plant is that once we turn it off, it still generates heat from the radioactive decay, and typically that's about 7% when it initially gets turned off. So the PRISM reactor has the ability to remove that heat very easily with air coming on the outside of the reactor vessel, and it can do that not for hours or days or weeks, but forever. And so that's the unique part of the design that we've come up with.
We saw in Fukushima that there was a problem with the coolant, and they were able to bring in seawater. Now, the seawater obviously ended up contaminated. It wasn't an ideal situation, lots of steam, and in fact it was the very hot steam that led to some of the explosions that people early on thought were a meltdown. Presumably with the sodium it will just continue to convect and continue to pass that heat out into the air, and we'll get lots of hot air, but nothing explosive, nothing building up pressure. So actually this will be a lot safer.
Yes. So if we look at what happened to Fukushima, they were in an event which we call beyond a station blackout. They lost all of their off-site alternating current, all their on-site alternating current, and all their batteries. And so they had to grapple with those operators to remove that heat, initially at 7% when they turn it off. So the way the PRISM is designed is that when it turns off, the way we remove the heat is we pipe in air right beside the reactor vessel. We have a different design, and that allows us to continuously remove that heat so we don't build it up.
And what fuels can a PRISM reactor actually use? What can you take advantage of?
One of the fuels we can take advantage of is the plutonium that has been separated in the United Kingdom during your reprocessing, and that has a great potential to produce a lot of electricity. The work that I've done in the United States, we looked at using this technology to extract fuel out of our used nuclear fuel. So that's another possibility. And then if you mixed some of our fuel with thorium, you could extract energy that way. So there's a lot of variants that you can do with PRISM as far as extracting energy from big atoms, is what we call it, to produce green electricity.
And what then happens to the fuel in there? Obviously, with traditional plants, you're left with quite radioactive, unpleasant stuff that we have a bit of a problem and a bit of an argument as to how we get rid of it. What's left at the end of the life of a PRISM reactor?
In the PRISM reactor that we have been talking to the U.S. government about, we take the fuel that comes out of the reactor, and we do a separations using electricity, not acids, but electricity. And when we do that separations, we take out what is called fission products. Those are the small atoms that when we break big atoms in half, like cesium, krypton, rubidium, Superman-type materials. And we put the elements that normally occur in nature as a mineral, we put that into a very robust ceramic. And then the other one that are normally as metals, we put that into a metal alloy. And those two waste products, this rock or ceramic and this piece of metal, then after about 300 years are less radioactive than the uranium ore.
So clearly it's a cleaner way of doing this as well, and we're going to have fewer dangerous products at the end of it. What sort of power can we get out of these PRISM reactors? Are they, again, equivalent to the reactors that we're currently seeing in service?
They're a little bit smaller. So what we have proposed for the United Kingdom for the disposition of the plutonium at the Sellafield site would be one PRISM power block, and its total electricity output is about 600 megawatts electric. And that 600 megawatts electric, over its lifetime, could disposition that plutonium that's currently stored at the Sellafield site.
So not only are you going to generate 600 megawatts of electricity, but you're also going to get rid of or use up or at least make use of a stockpile of plutonium that we currently have just taking up space and being a problem.
Yes, we turn that into an energy asset. We don't look at that plutonium as a waste, and your country's done a very good job of safely storing that plutonium for this future use. And the current policy, as I understand it in the UK, is that they don't want to reprocess or recycle like I described, so they just want to push it through a reactor system such as PRISM, extract some energy, and then place that in a geological repository. Now, if we took the full vision of the full capabilities of this technology, that 100 tons of plutonium could generate between 200 and 500 gigawatts of electricity. So there's a great energy potential there should it be chosen to be used.
Well, thank you very much. That was Dr. Eric Lewin he's the Chief Engineer at GE Hitachi.
And Eric will be with us for the rest of the show, so if you have any questions for him or for us, then get in touch.
You can tweet at Naked Scientists, write on our Facebook wall, or email chris@thenakedscientists.com. Once a nuclear power plant is commissioned, it's important to keep it running well and efficiently, and keeping the water flowing is just as important as maintaining the radioactive fuel. Heat exchangers are necessary to take the heat from the nuclear reaction and put it into water to make steam, which will then turn a turbine and generate your electricity. So heat exchangers rely on having hot water in one location and piping it through very small pipes which have a large surface area over which the heat can pass into the cooler water. Now that in itself creates a novel set of problems that scientists such as Birmingham University's Jonathan Morrison are trying to solve.
Well, the nut that we're trying to crack is the problem that's been seen in the nuclear industry for many, many years, which is deposition of corroded material at very small restrictions in systems. So as you go from a large flow, as you would having a flow directly from the core of a nuclear reactor and into the steam generator, you go from a very large flow into very small tubes. And you often see deposition at these very small tubes, the most inconvenient spot, which is right at the entrance of them as the water's entering the small flow regime.
How big a problem really is it? Does it cause a reactor to stop functioning properly?
Not so much stop functioning, it's more of a money issue. The worse it gets, the more often you have to shut the reactor off and clean it, because obviously you want to improve your efficiency, and the best way to do so is to have the best heat transfer at your steam generator and from your fuel rods. And you often have to switch the reactor off and clean it by hand in order to get this off. So this isn't something that would stop the reactor from functioning completely. This is merely money and the actual efficient operation of the plant. And it can also, if we can solve this problem, we can prevent people from having to clean it that often. And obviously the less time people have to clean it, the less material they're exposed to and the less dangerous environments they're exposed to. And that's a good thing all round.
So what is the material that's actually being deposited?
Well, that depends on what you've built your reactor out of. At the very beginning of the nuclear age, we used something called Admiralty brass, I believe, a type of copper-brass alloy, and that obviously would have deposited copper oxide and all sorts of things like that. In more recent years, we've moved from using that into using stainless steel, which has been an excellent material all round and is still used in many plants and is still used in conventional plants as well. But in more recent years, the most commonly used materials have been nickel-based alloys, which are extremely good. They're very good at corrosion resistance. They have lifetimes well in excess of many of the other materials we've used for the past 40, 50 years. And they are being increasingly found to be far superior to what we've used. My research is into stainless steel-based material, mainly because many plants around the world still have stainless steel steam generators, because replacing them with the new ones is really expensive. These things are hundreds of millions of pounds each. So if we can solve a problem and people don't have to replace their steam generators because of a failure, all the better.
Power plants that rely on other types of fuel essentially work in the same way by heating up water to generate steam to turn a turbine. So do we see the same problems in gas-fired plants and in coal-fired power plants?
Not so much. The issue with conventional plants, and by conventional plants I mean oil and coal and gas, they generally use something called a supercritical water, which means the water has been heated up above 374 degrees Celsius, and it's at a very specific pressure, which I can't remember off the top of my head. But what it means is that the water is no longer either liquid nor is it gas. It's actually in a completely new phase of its own. This new phase means that each unit of this water can carry a lot more heat than either steam or water liquid can carry on its own. So as you increase the temperature at which you're burning your fuel, And as you increase the temperature of your coolant, you're actually increasing the efficiency of the fuel that you've burnt. So you're getting more energy out of the same ton of coal or oil that you've burnt. Nuclear power stations don't work in the same way precisely. They do work by heating up water, but they don't work in the supercritical region because there is still a question of what will radiation do to water when it's heated up and when it's in the supercritical regime.
So it is really a nuclear bespoke problem that you're looking at. But what do you think is leading to this deposition being in those particular places where obviously it's going to disrupt the flow probably as much as it could do anywhere?
Well, there are many problems that it could be, but I've been charged with looking at a single specific one, which is a problem called the streaming current. And the streaming current comes from a corroded surface being exposed to flowing water that contains corroded particles. Now, the particles will sit very close to the wall, and as we flow water very quickly across the surface, these particles that are loosely adhered to the wall will be forced down the stream. As they're forced, they are flowing across the surface and they're generating something of a current. If you change the flow regime, that current is imbalanced, and in order to satisfy physics and the law of charge conservation, something has to happen in order for these particles and this charge to be balanced. So normally the particles will find themselves pulled back towards the surface and quite tightly adhered because they'll be reoxidized into another state. Now at this point you find that you have quite hard deposition around this point. Now where we normally see this is when you change the flow regime from being a large flow and into a small flow.
Do we have in the works any better ways to solve it rather than just cracking it open and cleaning them off?
No, unfortunately, the only way to clean these things is to get in there and manually do it. Not necessarily on your hands and knees with a pipe cleaner, but there are obviously methods to do it. But people have to be involved in cleaning the thing. There's very few sections of the reactor you can simply clean by putting some chemicals through it, and shoving some bleach through the steam generator isn't going to work.
And if you confirm that it is this induced current that attracts the particles in there, can we then use that to maybe aid future reactor design in order to reduce this problem?
Yes, the reactor design itself is not necessarily at fault, but it will need to be changed should this prove to be a really consequential problem. Over the course of reactor design, over the course of the last 50 years, has changed in order to redesign out a problem that they've seen. And water chemistry has been changed numerous times because of simple little things that we think, we can change that by changing the pH or just running it at a different temperature. This is just another one of those problems. Once this has been proven, there is probably more than likely a way to design the steam generator or to design any small flow restriction in a way that it will no longer be affected by this kind of thing.
Jonathan Morrison from the School of Chemical Engineering at the University of Birmingham.
Distilling the best science. The Naked Scientists.
This is The Naked Scientists with me, Ben Valsler, and with Dave Ansell. And still to come, we'll hear from both sides of the nuclear divide. Are nuclear power plants the solution to our energy needs, or a needless risk when renewable can provide our power? But first, the Messenger spacecraft completed 1 year of orbiting Mercury this month. Now, by that I mean 1 Earth year, not 1 Mercury year. And 2 papers published in the journal Science highlight some of the surprising scientific results from our solar system's innermost planet. Messenger launched back in 2004, and after a few successful flybys, it went into orbit around Mercury in March 2011. As well as taking lots of images, it's been measuring the magnetic field, taking spectral analysis of the surface and of its fairly tenuous atmosphere, and it's been mapping the terrain, and it's made some unexpected discoveries about the planet's surface and about its core. So using results from laser altimetry that was measuring topography, it becomes obvious that Mercury's northern hemisphere has a lower dynamic range of elevations, or it's simply less mountainous than Mars or the Moon. Now, that's not to say that Mercury has had an inactive life. There's plenty of evidence of meteorite bombardment and of volcanism, and also that large-scale changes have occurred since that last heavy bombardment, since the volcanic activity died down. Some impact craters have even been tilted on their side and distorted, and the middle of them are now higher than the edge of the crater. Now that suggests that either volcanic or some sort of tectonic activity must have been a very as yet poorly understood aspect of Mercury's evolution, so that's clearly a target for scientists to look at. Some of these unusual surface features, though, could be accounted for by Mercury's very strange core. It takes up 85% of the planet's radius. Now, that's much larger than we would predict from our understanding of Earth, where the core only accounts for about 50% of the radius. It contains a truly vast amount of iron, and that generates a fairly distinctive magnetic field, but it also has a very unusual structure. Earth has a solid inner core surrounded by a liquid outer, but it seems that Mercury has an extra layer of complication. There's a solid iron sulfide outer core that surrounds a liquid metal layer, and that in turn surrounds a solid inner core. That's partly why we get very strange magnetic signals from Mercury. This core structure is unique among all of the planets that we've been able to observe so far, but it does fit well with observations of the magnetic field, and it helps to explain some strange chemistry going on the surface. We know, for example, that the crust contains far more sulfur than could otherwise be predicted. So Mercury may yet have yet more surprises for us. Other reports also out this month have been hinting at the existence of frozen liquid water at the poles, for example, and due to its success, the MESSENGER program has been extended to probe even further, so we'll get yet more science in a few months' time.
Mercury is a very strange planet. It's very small and dense and just bizarre.
It is. It has the most uneven orbit of all of the planets, for example. It does things like rotates three times a year. It doesn't really fit with our current model of how planets evolve and how planets form in the first place. And that's why things like MESSENGER are really, really important. And that's why it's good that we understand what's going on in the core and the constituents, why there's all this sulfur on the surface, why there's all that iron inside.
And of course, the more we learn about the other planets, the more we understand our own planet itself. Now, on a completely different subject, a way of determining drug use from the sewers has been developed. Drug use in a population, both legal and illegal, is important to know about for health, social and even law and order reasons. And whilst it's relatively easy to keep tab on the amount of legal drug use by just going to a pharmacy and asking how much they've sold, the purveyors of illegal drugs are unsurprisingly rather reticent with this sort of information. And it's possible to study drug users with questionnaires, but they're also quite reticent, not necessarily accurate.
And I can imagine why people would lie about their drug use, but this isn't particularly new, is it? I found a report that said the River Po in Italy was analysed a little while ago, and it found evidence of consumption of, let me just check the figures, consumption of up to 1,500 kilograms of cocaine per year. So they're finding evidence, presumably metabolites of cocaine. What's the new angle here?
Well, that's fine for drugs which are only used for illegal reasons or can only be produced by legal means. There are quite a few drugs which are either used in legal uses and illegal ones, or can be created by metabolizing a legal drug into the illegal drug, and it gets excreted and ends up in the sewers as well.
I think there are some what we would call drugs that come from prescription drugs, and that of course is not to say that people have been abusing drugs. I'm thinking of amphetamines, which can often be breakdown products of prescription drugs.
That's exactly the problem. Now, Barbara Kasprick Holden and David Baker at the University of Huddersfield have been studying this, and they've used the fact, although both versions are often the same molecule, parts of these molecules can be mirror images of one another. And the legal and the illegal versions have different ratios of these different mirror images. And they've studied wastewater from a variety of treatment works using liquid chromatography machines to separate the different molecules and these enantiomers, the different mirror image versions, and mass spectrometry to give a better idea what the molecule is. They've found various different drugs in the wastewater, including amphetamine, methamphetamine, MDMA, which is ecstasy, ephedrine. But studying the percentages of the different enantiomers, the different mirror image versions, they can work out how much of each one of these was illegal and how much of it was legal. Technique is quite new. They need to do an awful lot of calibration because they don't really know how the different mirror image versions behave when they're in a sewer. You might find that some bacteria which eats one of them and doesn't eat the other one. So they need to calibrate the whole system at different temperatures and in different kinds of sewer. But it could turn into a very important tool in understanding just what is being used out in the population.
This is chirality, isn't it? Whether or not something left-handed or right-handed, a molecule can be one or the other. We know from other drugs that actually which-handedness they are can have a serious impact on how they work.
It certainly has an impact on the effect of the brain, and part of the reason why one version is legal and one version is illegal is that one has more psychoactive effects than the other one, and one of them might have more medical effects than the other one. So there tends to be this fingerprint between the different things ending up in different places. And the other thing, which this is important to know about, is the environmental consequences, because some of these drugs could have an effect on fish or the environment generally. So even the legal ones. So understanding this is also very important.
So that's one to keep an eye out, which handedness of drugs end up in the water system. Also this week, researchers at the Scripps Translational Science Institute in California have developed a blood test that may be capable of predicting an imminent heart attack. Publishing in Science Translational Medicine, Eric Topol and colleagues built on early work that shows that populations of unusual endothelial cells in blood samples taken from heart attack patients. These cells seem to come from the linings of arteries. So to find out why this was so interesting, Chris Smith spoke to Dr. Topol.
Well, we had a very big unmet need, and that is today we can't diagnose heart attacks that are incubating. It's very easy to diagnose a heart attack where there's already been damage to the heart muscle. So there's enzymes in the blood and there's a cardiogram that shows that. But the limiting factor is that we can't tell when the artery has cracked before the blood clot forms. It's a blood clot that causes the stoppage of blood flow to the heart muscle. So we want to know when that crack is occurring, which is a precursor to a heart attack.
So how did you approach that problem? We know that when someone has a heart attack, we have a narrowed area of a blood vessel which has an atheromatous deposit in it, and for some reason this atheromatous deposit ruptures or cracks open, and this forms a blood clot, which then blocks the vessel. So with that in mind, how did you approach saying, well, is there a way to try and preempt when this might be about to happen and who's at risk?
Yes, so back in 1999, there was the first paper ever that showed that these cells that were presumably coming from the artery lining could be found in the bloodstream before a heart attack. And so that was a very provocative paper that kind of sat dormant for, well over 12 years. Because we didn't really have, until more recently, the ability to unequivocally identify these cells, that they are truly coming from the artery, and also to zoom in on them and to do such things as sequencing and elaborate studies to understand what these cells are all about.
So what did you actually do? You have a group of patients who have a heart attack, you have another group of patients who are equivalent to the first group but haven't had a heart attack, and you compare the cells in the blood of both.
Right. So normally there's very few of these cells, if any, in a healthy person. And the cells are very, very elliptical. They're very one nucleus. They're very consistent. Whereas in the heart attack individuals from the early minutes of their blood had nothing to do with the heart attack per se. These are cells that clearly had to have been present for some days prior to that. But what was so unique about these cells is they were giant. They were very distorted and in clusters. And this is the first time that that's been demonstrated.
So let's piece this back together then. You get these blood samples from people who have had a heart attack, and it looks like these cells were probably in circulation prior to the time they had the heart attack. They could therefore be a warning sign that something's about to happen. How do you think they got from the diseased artery into the test tube that you tested?
Well, it's pretty straightforward. That there's a crack that's emerging in this inflamed segment of an artery from the surface of the heart. And that as the crack is growing before the blood clot forms, these cells are just getting shed from that spot right into the blood. And of course, once they're in the blood, just getting a blood tube sample is a window into that process.
It's reassuring that you found only a small number of these cells in healthy people. But of course, I wonder whether you included in that control group people who might have other risk factors but aren't having a heart attack. Because is there going to be a grey area where you'll have people who have artery disease but they're not at imminent risk of a heart attack, but your test looking for these cells might say they are?
Well, we haven't seen any grey area yet. We've extended this in many different patients, and we even took the healthy people and we kept having them come back, which had never been done before, to see how stable the finding is of their absence or relative absence of these cells. So we tried to drill down on that quite a bit, Chris.
The big question must be, well, how far in advance can we presage a forthcoming event and therefore intervene meaningfully in these people?
Well, this was a segue to a much more simple, quick, and hopefully quite inexpensive test. The work that we did was too laborious, trying to isolate all these cells. But now that we've done genomics of these cells and have a much easier signal to work with, we will take that to the emergency room setting to validate a practical test.
Wouldn't it be more meaningful to take a large group of individuals who are at risk and then just hoik them back into the clinic on a weekly basis and get blood from them, and then marry up those blood samples with the ones who do then over time go on to have a heart attack?
Yeah, that wouldn't work too well, because you'd have to do that in thousands of people every week to get the few relatively number that are going to have a heart attack. It's not so easy to find people who are about to have a heart attack that route. But if you go to the emergency room setting, where people, for example, in the U.S., there's 3 million people coming in with chest pain or tightness or pressure thinking they might have a heart attack each year. And out of those, so many have no damage to their heart muscle, but in fact are the exact kind of people that we're trying to identify, because they are having this precursor event. So that's a much better way than just taking people who are perfectly stable with no symptoms, having to come back to a clinic every week. But you're bringing up another point. This is a one-off test. In order to have the blood under surveillance all the time, in high-risk individuals like you were outlining, that will require a sensor embedded in the blood, which we're working on as well, that would communicate to one's smartphone to give a ringtone that a heart attack is incubating.
I'm also getting at the point that we're coming up with all these coronary risk profiles, and we're saying to people, you have a 10% risk or you have a 15% risk, and we're using this to inform what drugs we put people on. If we've got an even more acute measure, these are the individuals who are not just at risk, but these are really elaborating a heart attack. It's in evolution. Then they could actually be stratified for even more intense treatment, and a heart attack could be prevented in those individuals.
You've nailed it. The point is that once you know the heart attack underlying process is ongoing, it's a heart attack waiting to happen, then the main thing is to prevent the blood clot. If we prevent the blood clot, then the chance of preventing the event is exceptionally high. And that's really becomes the new goal.
Eric Topol from the Scripps Translational Science Institute at La Jolla, California.
Now, with a roundup of other science stories hitting the headlines this week, here's Mira Centelingam.
A new drug target to prevent male pattern baldness has been identified by scientists at the University of Pennsylvania. By profiling the genes and resulting proteins in scalp tissue from males suffering from the condition, George Kotsarellis found that in samples of balding tissue, there were increased levels of prostaglandin D2. It's thought the protein inhibits hair growth in hair follicles by acting on a receptor known as GPR44. Targeting this receptor therapeutically could treat or prevent male pattern baldness in the future.
If you look at the current treatments for male pattern baldness, they're all based on serendipitous findings. But what we've done is we've directly studied the disorder and looked for abnormalities in the actual scalp. And we showed that this protein inhibits hair growth in both human hair follicles as well as mouse hair follicles. We then identified the receptor that this protein works through, and there are compounds that target this receptor already. So we think that using these compounds would lead to a new treatment for male pattern baldness.
Satellite images have been used to identify over 9,000 sites of early human settlement in northeastern Syria. Researchers from Harvard University used computer algorithms to search the images for clues of human habitation, such as soil discoloration as a result of long-term human activity, and elevated mounds of land created by populations building on top of previous remains. Jason led the discovery.
This is significant because these places were not known before. We can now take this data set and we can ask really basic questions about the origins of settlement, the relationship of villages and cities to their environment. We can also take what we found and we can use this to protect these places in the face of new development threats, which grow every year. what's particularly exciting about the method that we've developed is if I were to do this on the ground, it would take me a very long time. With this method, I can map out the possible places of settlement very quickly.
Ibuprofen can reduce your chances of suffering from altitude sickness, which can cause symptoms such as headaches and nausea and can be fatal. Taking 86 volunteers up White Mountain in California to altitudes of 12,500 feet and dosing them with either ibuprofen or placebo, Grant Lippman from the Stanford University School of Medicine found that people taking the drug were 3 times less likely to show symptoms.
Up till now, the prevalent medications are prescription drugs like acetazolamide or dexamethasone, limited by prescription-only availability and each with side effects. So we're really excited about the generalizability of these findings that can affect the tourists and the weekend warriors and people who want to enjoy the mountains and don't want to be feeling awful for the first day or 2 days of their vacation.
And finally, black bears can heal their wounds during hibernation to emerge injury-free in the spring. By making small incisions in the skin of 14 black bears before hibernation and monitoring the state of these wounds as the bears hibernate through the winter, David Garchelis from the University of Minnesota found that despite having a lower metabolism during this time, the bears replaced layers of skin at injured sites and grew new hair with minimal scarring and no signs of infection.
Even though their skin temperature and their core temperature is greatly reduced and their blood circulation is greatly reduced, they are able to heal these wounds and have very little scarring on the wounds, and they even get follicle growth. All this is very different from other hibernators and obviously very different from humans, and we're hoping that if we can find out the mechanism that is used in bears to heal these wounds, maybe we can somehow apply it to help humans heal wounds, particularly when people don't have good circulation.
And the work was published this week in the Journal of Integrative Zoology.
That was Mira Senthilingam with our Naked Scientist Newsflash. Transcripts and the references for all our news this week can be found on our website at nakedscientist.com/news.
Thanks, Dave. Look to the sky and you'll probably see some frozen ice crystals and water droplets with fancy names like cumulus, cirrus or stratus, but you and I might just know them as clouds. But David Hooper is interested in very unusual noctilucent clouds that are only seen at certain times of the year. David carries out his research at the MST radar facility near Aberystwyth in Wales. MST stands for mesosphere, stratosphere and troposphere, but noctilucent clouds are found in just one of those atmospheric regions. Sue Nelson met up with David at his lab in Oxfordshire to find out more.
Noctilucent clouds are one of the rarest clouds that you're likely to see in the atmosphere, but at the same time it's something anybody, if they know when to go and look, can see. They form up at about 85 kilometres, which is very high up in the atmosphere. Most of the clouds you see day to day will only be in the lowest few kilometres and certainly not above 15 kilometres, so you're really much, much higher. The other thing is they only form during the midsummer months of June and July, and what we'd say is a middle and upper latitude, so anywhere in the British Isles you have the chance to see these. And you need to wait until the sun's set and gone a bit below the horizon. So dawn and dusk during the midsummer months, that's the time to go and see noctilucent clouds.
How can you tell a noctilucent cloud from, say, a cumulus cloud that everybody's familiar with, the fluffy ones?
You need to wait for the sun to set below the horizon. 85 kilometres, it takes a lot longer for the sun to set than it does on the ground. So you need to wait maybe half an hour after sunset. The word noctilucent itself means night shining. These clouds look sort of silvery. They're very often very thin, sort of filament structures, and you'll see them glowing, whereas the lower clouds, the typical clouds you'll see, will tend to be quite grey by then, if there are any.
In fact, you've got a picture for me here on your computer screen, and you're right, they are white and shiny and wispy and thread-like.
They do tend to be very characteristic, and all these small filaments are quite important. That said, it sometimes is possible to confuse a regular cloud with a noctilucent cloud, but if you've got nominally clear skies, you'll know if you do see a good example.
Why study these particular clouds?
These clouds are interesting because they're in a part of the atmosphere where it's quite hard to study anyway. So clouds, even low down, by watching what clouds are doing, it can tell you a bit about the atmosphere. But the other reason they're particularly of interest to scientists is nobody ever saw them or reports having seen them before, I think it's 1883, which was the time of the eruption of Krakatoa. And within a year or so of that, people started to report sightings of these, and there are indications that maybe they're becoming more common, and there is a bit of a suspicion that that could represent some indication of a change in climate up in the high part of the atmosphere.
So you've got these ice clouds at the edge of space. How do you study them?
We study not exactly the cloud, but we study a related phenomenon that we call mesosphere summer echoes. And we see this with the radar facility we operate in Aberystwyth.
And mesosphere being this area above the Earth where you specifically find these clouds.
Yeah, the mesosphere actually is quite a broad region. It stretches in altitude between about 50 and 90 kilometres. What we're looking at really here is the very top of the mesosphere, really right on the edge of the space environment.
So when you're using this radar array, are the echoes that the radar is detecting, are they echoes from the cloud itself, these noctilucent clouds?
It's not exactly the cloud, but we know that the cloud determines the echo. What we're really seeing in this part of the atmosphere with the radar are electrons, and this is from high-energy radiation from the sun splitting apart some of the molecules. What happens is these electrons get attached to the cloud, to the ice crystals, and what we're then seeing is the structure, which is driven by the electrons stuck on the ice cloud.
And by looking at the relationship between these echoes and the clouds themselves, what are you hoping to determine?
Well, to some extent, we're just trying to understand what we see with the radar. We run the radar most of the time to study the lower part of the atmosphere, what most people would call the weather. And we also see these echoes whether we like it or not. So my job really is to try and understand what these additional things we're seeing. Other people are more focused on studying the mesosphere and the regions of the atmosphere above that. So obviously any information we can give them in this very data-sparse region of the atmosphere is potentially going to be helpful.
So it's pretty exciting times then to study these noctilucent clouds.
Well, it certainly is for me, because for something we've been observing for 6 or nearly 7 years and never really quite understood what we're looking at, to suddenly see that there is something we can understand, that is exciting.
David Hooper talking to Sue Nelson about the promise of research into the weird and wonderful noctilucent clouds.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to Naked Scientists with Ben Valsler and Dave Ansell. We have a challenge to supply our growing demand for electricity whilst reducing our carbon emissions. Is nuclear power the only way to go? The answer is far from clear-cut. So to discuss some of the issues, Birmingham University organised a debate held in London this week. We sent Mira Senthalingham along to meet Ron Bailey, Parliamentary Consultant for the Association of the Conservation of Energy, but first she spoke to Professor Martin Freer, Director of Birmingham Centre for Nuclear Education and Research.
To my mind, there are 2 reasons that we need nuclear power. The first is to do with climate change, and the second is energy independence. So the climate change issue is that we need to reduce our CO2 emissions, greenhouse gas emissions, by 80% compared to 1990 levels by 2050. So you need to work out, of course, how you arrive at 20% on that sort of timescale. And a good reference marker for that is the work of the Committee on Climate Change. Now, what they've done is looked at the energy portfolio that we have now and potential energy portfolios for the future. And they looked at a number of different options, starting with the obvious one, which is renewable sources. They tried to work out what is the maximum amount of energy that you could get, maximum amount of power that you could get from those renewable sources. And it comes to about 40% of our energy budget on the timescale that we need. In addition to that, you could have something like 20% of gas. So things like wind turbines, they need backup energy supply, and that would come from gas generation. You need then another 40% coming from nuclear power.
And is nuclear able to provide that 40%?
So at the moment we have 15% of energy generation through nuclear power. To get up to 40%, I think, is a real challenge. The ability to build enough nuclear power stations, the number that we might need will exceed capability at the moment to build reactors.
Ron, what are your thoughts on this need for nuclear power to meet this extra 40% of energy that we need in the future?
The government did a lot of modelling about how to get both the CO2 reductions that Martin refers to of 80% by 2050 and to keep the lights on. And that modelling shows very conclusively that we don't need nuclear power to do it. There are at least 8 ways of doing it without nuclear power. That involves, obviously, investment in, firstly, energy efficiency, because the best energy is that you don't use in the first place, and renewables, wind, offshore wind, onshore wind, solar PV, biomass and combined heat and power, and obviously carbon capture and storage.
Martin?
I think the biggest issue is whether one can understand energy savings, energy efficiencies. And as yet, I haven't seen a substantial amount of research into the degree at which one can reduce from the current levels of energy consumption to the level at which one would need to reach in order to achieve the CO2 emissions targets.
What is the actual issue with energy today in terms of demand?
So if one looks back over time, so go back to the 1970s and look at how much demand has increased between 1970 and now, energy demand, electricity demand, has gone up about 1% per year. But if that linear trend continues, then we are going to see, over the next 40 years or so, an increase of 40% in our energy demand. At the moment, we cannot meet that in terms of the kind of capacity that we have, energy generation. One would need to make very dramatic energy savings just to offset that potential increase in demand.
Ron, though, for this increase in demand that's going to happen in the coming years, are these alternatives to nuclear plausible to actually meet such demand?
The government says that their figures are based on robust analysis. So the answer is yes.
But what about, as well as becoming more efficient with our energy, the actual alternatives and other renewable sources of energy?
Yes, of course, it's absolutely right. We can't just say we have to generate. And again, the government's evidence shows that these will provide enough heat and electricity to keep the lights on and to keep us warm in our homes.
One way of putting this into context is to take the evaluation done by David McKay. And he's looked at all the countries around the world to evaluate the amount of power per metre squared that you would need to generate. And for the UK, it's 1 watt per metre squared. And then you look at the amount of power that you could generate from a wind turbine, it's about 2 to 3 watts per metre squared, which means that to solve the UK's problems, you would need half to a third of the UK covered with wind turbines.
And how does nuclear compare to that?
Nuclear, of course, has a very high power density. You can get a gigawatt out of tens of square metres. So the power density is much, much higher.
Martin, just to focus in a little bit on nuclear power itself and some of the concerns just regarding the safety of future reactors, the actual designs of these future reactors, and the question of disposing of waste in these. So are these all being taken into account?
So you're right, safety is very important. And in fact, the nuclear industry has, surprisingly, a very good safety record. If you look at the types of power station which have been designed for the future, so EPR and AP1000, they're completely different in their concept of safety. They have a lot of passive safety features. This is using natural processes like convection to take over if an accident should happen inside a reactor.
And Ron, what are your thoughts on this?
On the issue of safety, I mean, the nuclear industry has been claiming it's very safe for years and years and years, and hopefully, and thankfully, there's some truth in that. But I can mention words like Fukushima, 3 Mile Island, and Chernobyl. So, it's not as safe as it's claimed.
Well, okay, so to put it into some context, if one looked at 3 Mile Island and looked at the number of people who actually lost their lives through that accident, well, it wasn't any. And indeed, if one looked at Fukushima as well, how many people died in the nuclear part of the event? Well, none. How many people died in the tsunami? Well, over 18,000. The worst nuclear incident, as Ron mentioned, was Chernobyl. Again, about 28 people died in that incident. And subsequently, the latest United Nations report in 2011 showed that only about 15 people got cancer, thyroid cancer, in the intervening year. So it's rather crass, but if one was to try and quantify how good that record is against other energy generators, then nuclear power is something like 100 times more safer than gas and 1,000 times more safe than coal.
To summarise, what should we be doing next? Martin?
I believe very strongly that nuclear power is part of the future. I think the government need to look carefully about the economic conditions, the political conditions, to encourage companies. It's a big gamble for companies to invest in nuclear power. One needs to make sure that those conditions are right.
Ron?
The next step is to fully investigate the potential for energy efficiency and energy saving, which hasn't been done. And as it's the cheapest, we should do that now. then we should start to invest in long-term renewables and low-carbon solutions, such as wind power, offshore wind, some onshore wind, biomass, combined heat and power, and carbon capture and storage. We can supply all our energy needs and reduce CO2 by those methods without nuclear power, which will be more costly.
Ron Bailey from the Association for the Conservation of Energy, and before him, Professor Martin Freer from the University of Birmingham. You can find the report Ron was talking about on the Department of Energy and Climate Change website to help you make up your own mind.
We are examining nuclear energy this week, and we're joined by Dr. Eric Loewen from GE Hitachi. Eric, thank you very much for staying with us. We've had a number of questions, but one topic seems to have come up over and over again in emails and on Facebook. People are asking about thorium. Now, could you just explain what thorium is and why it's even playing a role in this debate?
Thorium is element number 90. It's about 3 times more abundant than uranium. And thorium, if you put it inside a nuclear reactor, will absorb a neutron and turn into uranium-233, and then that becomes a fuel.
So it could be a useful thing to put into a nuclear reactor if we can get it to absorb those neutrons, if we can get it to play a part. Would it be safer? Would it be more useful? Are the byproducts less harmful?
I think we have to look at it from a resource standpoint. Since it's 3 times more abundant than uranium, it provides another energy input. So we have to provide a catalyst to turn that thorium into something that can be fissioned to break in half, and that catalyst becomes a neutron. So from a safety standpoint, from a waste standpoint, I really don't see, if you look at 10,000 feet, any real difference between a thorium or a uranium cycle.
So it's perhaps not the panacea that the internet seems to claim that it is.
Well, I think if you had a chance to read Sir David King's Smith School report on Towards a Low-Carbon Pathway, he talks about moving to a decarbonized society with more nuclear power and has discussions that there isn't enough uranium. And so that's where thorium can provide that extra element.
Well, thank you very much. Hopefully that will keep people talking, I guess, as it has had a lot of discussion. But we've also had a question on Twitter from Jean Shao, who asks what it is about newer plants that make them safer. So what have we learnt from the last 40 years of nuclear development in order to make safe plants?
We've learned to make designs that really take advantage of physics. It's probably misnamed called passive safety, but I would call it better using and understanding the physics, where we use gravity, natural convection, those sort of things to help cool the plant after it shuts down. So GE Hitachi's ESBWR has the ability to remove heat passively without any electricity, without any operator actions for well over 7 days. The PRISM reactor, while you had me on this show today, can do that for a very, very long time, if not forever. So that's where reactor vendors like GE Hitachi have learned to, what do we need to do to these designs to make them better and to make them safer?
We've also had a question from Eddie in Northampton, who was asking, what is the half-life of plutonium?
The half-life of plutonium, 239, is 2.4 times 10 to the 4th years. The other isotopes of plutonium have a little bit shorter half-life than that.
So that means that if you're breaking them down into plutonium down to something which has a half-life of only 300 years, that's definitely improving the sort of radioactive danger and pollution problem.
If you look at the repositories, they grapple with these long-term elements, and I call them transuranics, those elements above uranium, where they have half-lives of hundreds of thousands of years. That makes it tough on a repository design. If you get down to where you have fission products, which are on hundreds of years, then your repository design can be, I think, simpler and a little bit different.
And just to clear up a couple of the basics things, half-life essentially means that after that many years you will have half as much of the original product. So it doesn't mean that it will only last twice that length, because after that many years again, you have half again.
Right, but just to be clear for your listeners, if I have 1 kilogram of plutonium, I come back after one half-life, I'll have half a kilogram of plutonium and half a kilogram of uranium, because that plutonium decays into uranium.
Well, thank you ever so much for joining us. I'm sure that there are plenty more questions, and we can see more questions on Facebook. Dave, for some of the basics, we're talking about isotopes of things. So plutonium is an element. It comes in different isotopes. What do we really mean by that?
What defines an element is the number of protons it's got. So also the number of electrons it's got outside. So it defines the chemistry of that element. You can then change the number of neutrons inside that atom, and that will change its nuclear properties, won't change its chemical properties, and these things with different nuclear properties are called isotopes of an element.
So it's still the same element, but different numbers of neutrons. So the 238 is the number of neutrons.
The 238 is the total mass, the total number of protons and neutrons. And so 239 will have an extra neutron or whatever.
Excellent. And now with a super hot question of the week, we're joined by Hannah Critchlow.
The Naked Scientist's Question of the Week, brought to you in association with the How to Wisman Foundation, supporting science and education from Alpha to Omega.
This week we hear from a listener who wonders about the inequality of the temperature scale.
Well, I'm Bronwyn Higgs and I'm based in Melbourne, Australia. If we have a lower limit on temperature that is absolute zero, where it's so cold that nothing happens, why do we not have an upper limit?
We turn to Sam Gregson, high-energy particle physicist at the University of Cambridge and working at the Large Hadron Collider in CERN, Switzerland.
The temperature of a system is simply related to the amount of energy in that system. Because a system can't have a negative energy, there is only so much heat you can remove from it, and so a limit to how cold you can get. This is called absolute zero. We have got very close to it. Scientists in Finland have cooled rhodium atoms to 1/10 of a billionth of a degree above absolute zero. On the other hand, an absolute maximum temperature would require there to be a limit to the amount of energy you can give to a particle. As far as we know, there is no such limit. Although the speed of light is the universal speed limit, the reason you can't get there is that this would require an infinite amount of energy. So this speed limit does not limit the amount of energy and therefore the temperature of an individual particle. The most energetic particle ever observed was a cosmic ray of a UTAR travelling at 99.999999985% of the speed of light, probably a single proton with about 50 joules of energy. This is equivalent to about 5 trillion degrees Celsius, and there is no evidence that this is the hottest you could get to. As far as we know, you are just limited by the amount of energy you can give to a particle. So you could say that the absolute maximum temperature is a temperature equivalent to all the energy in the universe concentrated onto one particle. But that limit's more accounting than basic physics.
Thanks, Sam Gregson from Cambridge and CERN. So temperature is related to thermal energy. And Einstein's theory of relativity means that although a particle has a universal speed limit, it doesn't have an energy limit. So, if you took all of the energy in the universe and put it into one particle, you'd essentially run out of energy before you run out of capacity for energy, which is why we have no absolute maximum temperature. And linked to energy consumption and capacity, let's roll over to next week's question.
Hello, this is Christian Leixenring and I'm from Bielefeld, Germany. So, at times I'm really hungry, feeling shaky because of my low blood sugar and all. I'm wondering though, why my stupid body doesn't realize that there are plenty of nutrients around my waist, so I would neither have to feel bad nor to run for a cheese sandwich. So why is it that I feel so abhorrently hungry when there's enough to digest without actually involving my digestive tract? Thanks a lot for the answer and goodbye.
Send your thoughts to Chris at thenakedscientist.com, tweet at Naked Scientists, write on our Facebook page or join in the debate on our forum, which is at nakedscientist.com/forum.
Thank you very much to Hannah Critchlow with our question of the week. And that's all we have time for this week. Next week we'll be tipping out the mailbag and opening the phone lines because it's a question and answer show. If you'd like to get in touch, you can email your questions to chris at thenakedscientists.com. You can tweet at Naked Scientists or post them to our Facebook page. That's at thenakedscientist.com/Facebook. Thanks to Eric Lowen, Jonathan Morrison, Ron Bailey and Martin Freer, and to our production team of Mira Senthilingam, Hannah Critchlow and Tom Simpkins. We'll be back next week.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.